Hello, thanks for joining for today's session. This is week 11 of the problem solving session, and we'll continue with few more types of energy balance problems. But here, since the chemical reaction is also happening, so we'll have to combine the principles of material balance with energy balance in order to solve these problems. Okay. Myself, Mohchandra. I'm a PhD scholar in the Department of Chemical Engineering at IIT Kanpur, and I'm working in the area of tissue engineering. Again, feel free to reach out to me. This is my email, and post your queries if you have any in the course discussion forum. So, for the past 11 weeks, this is the 11th week, we are meeting on every Saturday from 3 to 5 p.m. The next week, coming week, will be the last session as well. The recordings are available in my YouTube channel. You can check it out. Also, the notes are made available to you in your NPTEL platform after you log in. So let's begin with the first problem. Here we have to calculate the heating value of coal. So what it states, coal gasification consists of chemical transformation of solid coal into gas. The heating values of coal differ, but the higher the heating value, higher the value of gas produced. Essentially, methane, carbon monoxide, hydrogen are the components of those gas. The following coal has a reported heating value of 29,770 kilojoule per kg. Okay. Assume that this is the gross complete heating value. So calculate the net heating value. Here, one thing we have to consider when we are talking about heating value, it means that the coal is being burned and whatever heat that is generated is basically your heating value. This value that they have given is the gross one, but we have to consider the fact that during burning, some water also gets generated. Coal is essentially carbon. So when you combine carbon with oxygen, you will get CO2, right? And it also has some hydrogen as well. This is a component of the coal. So it has some hydrogen component as well. So some water will also get produced. So in this burning process, this water is getting produced. So we have to first calculate how much is the quantity of this water and then calculate what is the energy required to evaporate this water in order to get only heat. So whatever energy that is being used to evaporate this, that energy will get subtracted from the gross value and then you will get the net heating value. Okay, so let's do this. So let's consider a basis of 100 kg of coal. Since the composition is given as 100%, so if there is 100 kg of coal, then we can say that, let's say 5.6 kg of H2 is there, or 13.0 kg of O2 is there. Okay, so let's then calculate what is the amount of water formed during combustion. So the main component will be hydrogen. Hydrogen will contribute to it. So there is 5.6 kg of hydrogen. Okay. For yes. And then 1 kg mole of hydrogen basically corresponds to 2 kg of hydrogen, and for water, and 1 kg mole of water will be generated for every 1 kg mole of hydrogen, and 1 kg mole of water is basically equivalent to 18 kg of water. Right? This is the expression that we have to solve. So if you see, if I cancel out the common terms, then we would get how much kg of water will be there. If we quickly do calculation, the remaining number part, it should be equivalent to, you also do it, all right? So it should be equivalent to 50.4 kg water. Okay. So what's the heat or energy required to evaporate this water? So for this, we have to take the value of latent heat of vaporization of water at 25 degrees Celsius. Okay, if you see your properties table and all, that value should be 2442 kg kilojoule per kg. So we'll use this value to calculate the energy required to evaporate 50 kg of water. So this should be, let's calculate. One two 3076.8 kilojoule. Right. Now we were given in the basis for 100 kg of coal. How much is the energy required then? This is for per kg, right? For per kg. Sorry. This is the energy required to evaporate 50 kg of water. Now this 50 kg of water will be generated when you burn 100 kg of coal. So for per 100 kg of coal, if I say what is the energy required, it will be divided by 100 kg. So it should be 1230.77 kilojoule per kg. Okay. So we were given gross value, gross heating value as this. $29,770 kilojoule per kg. So net heating value will be 29770 minus 1230.77. Let's calculate. It is 28,539.23 kilojoule per kg. All right, so this is the net heating value. Sounds simple, right? Now let's move on to the next question. So here you have to calculate the standard heat of formation for incomplete reactions. So there is an iron pyrite ore that contains 85% FeS2, 15% Gangue, which is basically inert rock, dirt, etc. Is is roasted with an amount of air equal to 200% excess air, according to the reaction this one. Okay, 200% excess. In order to produce SO2, all the Gangue plus Fe2O3, they end up as solid waste, and it also contains some unburnt Fe2S2 that is around 4%. So you determine standard heat of reaction per kg of ore. Okay. So before we begin, let's start with the basis. That is 100 kg of ore for 100 kg of ore. What are the ore components? Let's tabulate that. Ore contains FeS2 and Gangue. What is kg? Now it is given in percent. So 100% equivalent to 100 kg. So similarly, FeS2 will be 85 kgs and Gangue will be 15 kg. If you want to convert this kg or mass into number of moles, we have to take the molecular weights. So molecular weight of FeS2 is 120. Gangue, you don't know. So what is then number of moles? So we will calculate it as kg mole. So this will be 85 by 120. So it is 0.708. Correct? It's for FeS2. We started with 0.708 kg mole of FeS2. Now, how much oxygen is required for this combustion reaction? Required oxygen. So, if this much is entering, this much of FeS2 is entering, iron sulfide is entering, and if the reaction proceeds according to this stoichiometry, that is for 4 kg mole of FeS2, you need 11 kg mole of oxygen. This is the basically this will give you what? This will give you required amount of kg mole of oxygen. Let's calculate that. It is 1.95. Okay, this much kg mole of oxygen is required. But how much oxygen is entering now? This is required. Okay, and 200% is excess. So 200% means 2 into 1.95. So this is the total amount of oxygen that is entering. If we calculate it, it's come out to be 5.85 kg mole. Okay, kg mole oxygen entering. So air is entering, right? So another component of air is nitrogen. So entering nitrogen. So you know in air there is 78-79% nitrogen and rest 21% is oxygen. So if we take this fraction and multiply it with 5.85, okay, so what you will get? You will get the nitrogen, kg mole nitrogen entering. It is, we do the calculation, you should get, you just give me a second, should get close to 22 kg mole of N2 is entering. Okay, this is the composition of ore that is entering, and then you also calculated how much oxygen is required, and right, and how much oxygen is entering. Now if we look at the solid waste part, solid waste, it contains three components: Gangue, Fe2O3 and FeS2. Let me take a new page. Solid waste. So as I said, it contains Fe2O3, Gangue, and FeS2. This FeS2 is basically unburned, which is not burned, which has not burned, it is becoming part of the waste. So for the same basis, that is 100 kg of ore, let X be the kg of FeS2 that has unburned. Okay, this means FeS2 in kgs, if we write solid waste component and kgs. First is FeS2 is X, Gangue. So Gangue is inert. 15 kg was entering in the ore. So in the waste also, it will stay 15 kg. What about Fe2O3 is which is one of the product in this reaction. So this you will have to calculate. So how do we calculate this? Let me do it here. So if X kg of Fe2S2. Fe2S2 is unburned. So how much kg of Fe2S2 is burned then? In the ore, there was 85 kg minus x. 85 minus x is the kg Fe2S2 burned. Now, for every 4 mole of Fe2S2, let's write as 4 kg mole of Fe2S2, you need 2 kg mole of Fe2O3. Okay. Now let's convert this kilomoles into kgs. So you know 1 kg mole of Fe2S2 contains 120 kg Fe2S2, already mentioned, whereas the molecular weight of Fe2O3 is 160. So 160 kg of Fe2O3 corresponds to 1 kg mole of Fe2O3. So if you remove the common terms here, you will get the answer in kg Fe2O3. Now, thing is, there is a variable x. So you cannot fully solve it, but you will get an expression in terms of x. So what it will be? 1 by 2, 8 by 6, or 85 minus x into 2 by 3 kg Fe2O3. This is the value that should come here. Eighty-five minus x into 2 by 3. Okay. Now we are told that solid waste contains 4% Fe2, FeS2, 4% FeS2. So this means 0.04. So we can form an expression basically in terms of x, that using that you can get the value of x. So 0.04 is equals to x is the amount of, or we considered x to be the amount of FeS2 unburned. So x by x plus 15 plus 85 minus x into 2 by 3. So this is basically the expression that we wrote from our understanding of mass fractions. This 4% is nothing but 0.04 mass fraction, right, for FeS2. That is how we wrote this expression. Now, we have to solve this expression to get the value of x. So let's quickly do that. While you are seeing me on the screen doing it, I urge you to do it with me. So I've like brought all the x terms and constant terms together. So x is coming out to be 2.9331. Let's write it as 2.93 kg. Okay, this is the amount of or the mass of FeS2 unburned. So what is the amount of Fe2O3 that is produced? 385 minus 2.93 into 2 by 3 is 54.7 kgs. Okay, so overall then this is the compositions that we wrote. So if we substitute here the values of x with 2.93 and this expression of Fe2O3 as 54.7, and we know the molecular weight of FeS2 is 120 and this is 160. Then what is kg moles? Then individual kg moles. 2.93 by 120 and this is 54.7 by 160. This is coming out to be 0.024 and the other value is 0.342. All right, so this is the kg moles. Now, you know the amount of FeS2 that is unburned, and that means it is part of the waste. So, what is the amount of FeS2 that has burned or oxidized? So it will be 85 minus 2.93. It's 82.07 kgs. Now, if we convert it into gram moles, we know 120 kg of FeS2 corresponds to 1 kg mole of FeS2. So this will give us 0.6834. 0.684. 0.684. Okay. So now for this much of moles of FeS2 burned, what is the corresponding or required kg mole of gases that is produced or used? So O2 is used and SO2 is produced. I have to calculate that. So O2 used. So you have to use the stoichiometry here. So for 0.684 kg mole of FeS2 that is burned, and this reaction proceeds according to stoichiometry, and stoichiometry says that it needs 11 moles of O2 for 4 moles of FeS2. Okay, so this will give you 1.88 kg mole. All right, this is the oxygen used. And what about SO2 that is produced? So for burning 0.684 kg mole of FeS2, this is, you need 4 moles of FeS2 to generate 8 moles of SO2. 8 kg mole SO2. So it is 1.368 kg moles. Now we know the value of number of moles for every component that is being used in this reaction. Now in order to calculate the heat, just that is the question, right? If you remember, this question states you have to determine the standard heat of reaction per kg of ore. So in order to do this, we have to refer to the heat of formation table that we already discussed in the last week's session, right? Here from this table, you can get the minus delta HF values or heat of formation values of all the components involved in this reaction. So let's compile them. So what are the components that is involved here? It is FeS2, O2, Fe2O3, and SO2. So negative delta H F. So this is the heat of formation under standard condition. In the units of kg, in the units of kilojoule per gram mole. Kilojoule per gram mole. Okay. So for FeS2, this is FeS2. It is saying to see iron sulfide. So iron sulfide is this. It is in form C. All right. So state C. This value is 177.9. So remember there is a minus sign. So when we'll do the further calculation, we have to incorporate this minus sign here, all right, in front of the value. For oxygen, the heat of formation is 0. For Fe2O3, this is Fe2O3, ferric oxide is 822.156. And for SO2, is given here, sulfur dioxide SO2 in gas form. It is 296. Sorry, I was just checking something. So it is 296.9. Right? So it is in gas form. So for convenience, let's write this as a state for which we have taken these values. So we have the heat of formations with us. Now let's calculate the standard heat of reaction. This basically standard heat of reaction for products minus for reactants, right? And here there will be number of moles as well. This is the expression that we have to use for calculation. So in the product side, our product is Fe2O3 and SO2. These two are the products. So the number of moles for Fe2O3 is, let me highlight it, it is 0.342. Fe2O3. Then for SO2, the number of moles that is produced is 1.368. And what is their heat of formations? So for Fe2O3, it is minus. Remember, there's a minus sign here. Minus 822.156. And for SO2, it is minus 296.9. This is the product side. We have to subtract the reactant side from this value. So in the reactant side, there are remaining two components, FeS2 and O2. So number of moles of FeS2, we calculated two values. One, how much is supplied initially, FeS2. Then we calculated number of moles that is unburned, that did not burn, all right, and became part of your solid waste. But for the calculation of heat of reaction, we will use the number of moles of FeS2 that has actually burned, that is oxidized. This value we will use 0.684. And for oxygen that is used, number of moles that is used for this reaction is 1.88. Let's put the values of heat of formation. So for FeS2 it is minus 1779, and for oxygen it is 0. It's for the reactants. Once you solve this, you will get the value of the heat of formation basically in kilojoule, right? Now the thing is, there is a unit difference. The number of moles that we calculated were in kg mole, all right? And here the heat of formation values that we took from the table is in kilojoule per gram mole. So we have to make convert the other way, gram to kg is better, because we have then what do you say, divided by the divided with the total amount of ore that we have, that is 100 kg. So if we just remove it, the moles altogether, so it should give you a value in kilojoule. So in order to do that, we have to like multiply it with 1000. This entire thing will get multiplied with 1000. Why? And 1 kg mole is equivalent to 1000 gram moles, and we have kilojoule gram mole. So gram mole gets divided, this cancelled, this get cancelled. So this 1000 value remains. So if we multiply this entire expression with 1000, we will get the answer in kilojoule. The final answer that we'll get will get divided by 100 because it is the kg of ore that we need, right? So that should, and the final answer should have a unit of kilojoule per kg ore. I hope this part made sense to you, right? Now let's quickly do that. Do this calculation. So we are getting minus 565,653. Okay. And once we divide it by 100, we'll get minus 565.6.53. So this should be the answer. Okay. In kilojoule per kg ore. The standard heat of reaction. Understood? So before we move on, let's take a quick break of 2 minutes. All right, then we'll solve the rest of the problems. So I have only two more problems left, and I think we'll cover it up with, yeah, within the time we have remaining. All right. Hello. So let's begin with the next problem. So here you have to calculate the heat of reaction at a temperature which is not your standard temperature, like not at 25 degrees Celsius. Okay, at a temperature that is different from the standard conditions. So in order to uh, do this, let's quickly understand a small concept. So at steady state means when there is no energy accumulation, for zero change in kinetic energy and potential energy, and also when the shaft work is zero, then what? Then Q becomes equals to delta H, which is the energy balance equation. All right. When we want to calculate, let's say this is at temperature T. Okay, so let's write it as delta HT, or just write this since we want to represent it as a heat of the reaction, so delta HRT. All right, and this is basically change in enthalpy in products minus change in enthalpy of reactants. This you already know, but with this an additional terms get added, which is standard enthalpy, uh, standard accepted condition, change in enthalpy standard condition. So, or rather than writing a standard, let's write it as reference, T reference. Okay. So if your reference temperature is 25 degrees Celsius, then this term is basically the standard one. And with this, we multiply it with the extent of reaction, right? To account for the chemical reaction that is going on. Now, this term, how do we solve? We have to use the definition of H is equals to CPDT, right? Delta H is equals to CPDT, sorry, CP delta T. We have to use this definition. Then if we use that, it becomes delta Cp dt integral. Okay, differential. I'm putting dt, so I'm putting an integral sign. And this will give this delta Cp, let's say, has a form of alpha t plus beta t, alpha plus beta t plus gamma t square, something like that, something of that sort of form. Then it will become alpha delta alpha t plus delta beta by 2 t square delta gamma by 3 t cube and some integral constant c. Let's substitute this here. Plus the heat of reaction at reference temperature R ref. That's a better notation. Heat of reaction at reference temperature. Now these two, let's club these two terms as delta H naught, okay, plus the remaining terms. Okay, this is your heat of reaction at temperature T, at any temperature T. So we have to use this expression to solve the given problem. Okay. Now the problem states the inventor thinks he has developed a new catalyst that can make the gas phase reaction, this is the reaction, proceed with 100% conversion. So 100% conversion into the fact that extent of the reaction is 1. So estimate the heat that must be provided or removed. So Q can be either positive or negative value if the gases enter and leave at 500 degrees Celsius. So you have to basically calculate the heat of the reaction at temperature 500 degrees Celsius. And 500 degrees Celsius is equivalent to 773 Kelvin. All right. So we have to calculate the heat of the reaction at 773 Kelvin. So let's begin. The reaction is CO2 plus 4H2 gives 2H2O plus CH4. This is the reaction. Let's consider a basis of 1 gram mole of CO2. That is the basis. And if we use the this table, the heat of formation and heat of combustion table, to get the heat of formation for each of the components involved in this reaction, let's do that. Minus of delta H hat. This, it is in kilojoule per gram mole. The values that we'll get from this table is in kilojoule per gram mole. So first is so heat of formation of H2O is 0. All right. This is in gas form. Water is also in gas form. Methane is also in gas form. CO2 is also in gas form. So for CO2, the heat of formation is 393.51. 393.51. Then H2O, it is 241.826. And for methane, it is 74.84. All right. So with this values, you can calculate the heat of reaction at temperature 25 degrees Celsius or 298 Kelvin. Okay, that is 25 degrees Celsius. So what it will be, the product side, there is 2 moles of H2O minus 241.826 plus minus 74.84 products minus for CO2 it is minus 393.51. For H2 it is 0. So this will become, let's do the calculation. It is minus 164.982 kilojoule per gram mole. All right, this is the heat of reaction at standard conditions. Now we have to get these values delta alpha, delta beta, delta gamma. Okay, so for doing that, we have to use the heat capacity table and get the CP equations for each of the components. All right. For CO2, H2, H2O, and another component is methane, CH4. Cp is equals to for CO2. So we will take the values in degree Celsius here because I see that they have given values in either Kelvin or degree Celsius. We'll have to take the value at degree Celsius. So for sake of consistency, let's consider degree Celsius in our discussion at all times. All right. So for Cp of CO2, it is at 6.1. So all of these Cp values that we'll calculate has a unit of kilojoule per mole degree Celsius. Okay. Keeping in track with the units is very important. It helps you understand if you are going wrong somewhere. So for CO2, it is 36.11 in 10 to the power minus 3. This is alpha or A term, then 4.233 into 10 to the power 5. This is the B term or beta. Next is C term, so it is minus 2.887. into 10 raised to the power minus 8 t square plus 7.464 raised to power minus 12 t cube, right? Then similarly for others, let's quickly write it one by one. So for hydrogen, in degrees Celsius, this is the values 28.84 raised to power minus 3, 0.00765 raised to power minus 5 t, 0.3288 raised to power minus 8 t squared plus 1 minus 0.8698. 8698 raised to power minus 12 t cube. Then after hydrogen, water, in gas state. $33.46 plus 0.6880 plus 0.7604 plus or minus 3.53593. 3.593. For methane, it is 34.31, 5.469, point 3661 minus 11. All right. A, B, C, and this is the fourth term. So we can calculate delta A to be addition of these terms. So here delta A will be calculated in the same way as you calculate delta H. So delta A or delta alpha will be for the product and then the reactant side. Here products are water and methane. So 2 into minus 3, methane 34.31 in 10 to the power minus 3. Rather, here what we can do, we can keep 10 to the power minus 3 outside. Plus minus the product's reactant side, CO2 and 4H2O. Four into 28.84. This is delta A. We'll calculate this value in a minute. First, write similar expressions for delta B. Okay. So for delta B, go into for water 0.688 plus methane 5.469 minus reactant side 4.233 plus 4 into 0.00765. Then for delta C, 2 into for water, then for methane, okay. So we have written delta values, expression for calculating delta values. Let's quickly do that. So we have calculated the delta A, B, C, and D values. So we can, what we can do next, we can, so the final value of delta CP will be, let's like write a combined equation. So this was delta CP, only del gamma. So let's substitute in this expression delta A, delta B, delta C, right? There will be one more term here, delta D. Now there is, in our expression, there is TQ. So when we integrate it, become T is to the power 4 by 4 plus C plus this. Okay. So delta CP is minus 50.24 plus 2.5814. Yeah, this will be written as T here, then plus 3.4587 lastly the delta D term, which is minus 22.1708 EQ. Okay, this is your overall expression for delta CP. So at 25 degrees Celsius, if you apply this expression, then you will be able to calculate delta H naught. Because at 25 degrees Celsius, you know the heat of the reaction. You will just put the values of T here and will get the value of this whole thing. And then you'll be able to get the value of delta H naught. So delta H naught is basically the heat of the reaction at 25 degrees Celsius minus this terms. Delta A T minus delta B T squared by 2 minus delta C cube by 3 minus delta D T is to the power 4 by 4. Okay. So we are getting, we got at 25 degrees Celsius heat of the reaction as minus 164.982 minus delta A values is given here, and your T is 25. B value is this. C value is this, and lastly it is D value, delta D value. Yeah. This is a quite big equation. So you can use your scientific calculator to solve this. So you should get close to 164, 163.734, the units of kilojoule per gram mole. Yeah. Now you got the constant value. So at 500 degrees Celsius, the heat of reaction will be the heat of reaction at 25 degrees Celsius plus this value. Which is 1.24775. This delta AT, delta BT squared, this whole value is around this. So if we add it, oh no, I've done a very silly mistake. So here the temperature is 500 degrees Celsius, right? So you have to recalculate this expression for T is equals to 500. Okay. Then the value will become 20.79854. Yep. So when you add this to, you should get minus 44, minus 144.1834, close to this value. Right. In the units, kilojoule per gram mole. So this indicates what? This indicates heat is removed, right? Negative value is there. This much heat is removed for the reaction that is undergoing reaction at 500 degrees Celsius. Okay. So yeah, that was pretty lengthy problem. So we have We are almost towards the end of today's session. So I have one more question left. Let's quickly try to complete it. So this is the energy balance on an adiabatic reactor. Here the dehydrogenation of ethanol to form acetaldehyde, this is acetaldehyde, CH3CHO, is this undergoes through this reaction where ethanol in vapor state is converted to acetaldehyde and H2 and is carried out in a continuous adiabatic reactor. Hence Q is equals to 0. Alright. Ethanol vapor is fed to the reactor at 350 degrees Celsius and a conversion of 50% is obtained. So calculate the product temperature. So for doing this problem, we have to use this equation only, this one. Okay. So let's begin. So this is the adiabatic reactor. And let me start it from a fresh page. Let's consider first a basis of 100 mole of C2H5OH, 100 mole of ethanol, or a better way is to write 100 mole of feed. Feed contains ethanol, so yeah. So if we draw a flow chart, this is your adiabatic reactor and 100 mole of C2H5OH is entering, okay, at temperature 350 degrees Celsius, and it is in vapor state. What is coming out? Acetaldehyde, which is CH3CHO in vapor state, H2 in gas state, and some ethanol will also come out, C2H5OH. Because 100% conversion is not there, 50% conversion is there. So 50% conversion is there, that means 100 mole is entering, so 50 mole of ethanol will come out and rest 50 mole will convert to acetaldehyde. Okay. And on the basis of your stoichiometry, for 1 mole of acetaldehyde, you also produce 1 mole of hydrogen. So 50 mole of hydrogen will also be produced. The temperature of this product stream will be, let's say, at temperature T ADR in degrees Celsius. Or let me write it as T AD degrees Celsius. All right. So let's assume some variables to represent the enthalpy values or specific enthalpy values of each of the components. So for this reaction, let's consider a reference state of 25 degrees Celsius and 1 atm pressure. So acetaldehyde, H2, and C2H5. These are the substances involved in this reaction. Now, number of mole that is coming in and enthalpy that is coming in. The unit of number of moles is N is mole and it is kilojoule per mole, right? Similarly, out in the product side basically. What is coming in? C2H5 is coming in. How many moles? 100 moles. And let's represent its enthalpy as H1 hat. Okay, this is not applicable here. What is coming out? Acetaldehyde is coming out as 50 mole. Let's consider its enthalpy to be H2. Hydrogen is also coming out with 50 moles. Enthalpy representation with H3. This is with 50 moles. Okay, and let's represent its enthalpy as H4 hat. Since this is an adiabatic reaction or adiabatic process, Q is equals to 0. And from energy balance equation, under condition where enthalpy steady state is there, means no accumulation, no potential energy, no change in kinetic energy, all are 0. Work is also 0. Then Q is equals to delta H. So this implies change in enthalpy, that is Q. This overall process is 0. All right. So let's write as H delta H as the HR, as the heat of the reaction, is equivalent to is equal to this expression. No. Um, Now here the thing is, we cannot directly use this expression because here the extent of the reaction is not going to be 1. So we will use this form instead, this form of the expression instead. All right. So delta HR is basically product side minus reactants, all right, plus the extent of the reaction into under standard condition, what is the heat of the reaction. So first, let's calculate the extent of the reaction. So you see, number of moles of acetaldehyde CH3CHO is coming out minus number of moles of acetaldehyde going in divided by the stoichiometric coefficient of CH3CHO. So what is 50 moles is coming out, nothing is going in, and the stoichiometric coefficient is for this particular reaction is 1. So it is 50 moles. Okay. Then standard heat of reaction. How would you calculate? We have to take the values of standard heat of formation here. So First write the expression the similar manner. Ni standard heat of formation for products minus Ni standard heat of formation for reactants. This is the equation that we will follow. Okay, sorry, here we don't use Ni. We use stoichiometric coefficients. Sorry, my bad. Of each of the components. Okay. So on the product side, there is acetaldehyde and H2. So for acetaldehyde, the stoichiometric coefficient is 1. But what about its heat of formation? So heat of formation is minus 166.4. Okay. Then for hydrogen, the heat of formation is 0. This is the product side. Then in the reactants, there is only one component, which is ethanol. The heat of formation of ethanol, ethyl alcohol, is minus 277.63. All right. So this gives us one triple 1.23. Oh, sorry. By mistake I took the value of ethyl alcohol in liquid state, but we should have taken in the gaseous state. So it was 235.31. So it is 68.91 kilojoule per gram mole. Yeah. So you must take the values properly by saying which state you require it. So in our reaction, all the component is in gaseous state. So this is the standard one we got. Um, we got, so that means in this particular expression, extent of reaction into heat, standard heat of reaction, we got it, right? Now we have to calculate the remaining two terms. So for inlet enthalpy, or the enthalpy is associated with the reactants, Here only one reactant is there, right? Ethanol. So for calculating Ni, is ethanol, C2H5OH. We have to get the value of H1, right? H1 hat. How we will calculate it? We will calculate it from the heat capacity equation, Cp, and we will integrate with respect to T from temperature 25 to 350 degrees Celsius. 25 degrees Celsius is your reference state, and it will, and then since the ethanol is fed at 350 degrees Celsius, so it will integrate it to 350. Okay, so let's do that. What is the value of Cp here? For ethanol, ethyl alcohol. The state is gas. I found it, so let's write it down. So here H1 hat is 28.34 kilojoule per gram mole. Kilojoule per mole, sorry. The unit will be kilojoule per mole. Okay. This H1 hat. Now, in the outside, we have to consider that T is the temperature. T adiabatic is the temperature at which it is coming out. So we will get expressions for H2 hat, H3 hat, and H4 hat. First, let's do for acetaldehyde. For acetaldehyde, let's see CP if it is given. Okay, in this table it is not given, but in the textbook from which I have taken this problem, they have given this CP value. The reference date will be 25 to T. Okay, diabetic. So CP is 0.05048 plus 1.326 into 10 to the power minus 40 minus 8.050 to 10 to the power minus 8 T square and 2.380 10 to the power minus 11 T cube dt. Okay, so when you solve it, you will see you will get some values as this. I'm also simplifying it. So yes, this value will come out to be 0.05048 adiabatic plus 6.63 into 10 raised to the power minus 5 a square adiabatic minus 2.683 10 to the power minus 8 a cube adiabatic plus 5.95 10 to the power 12 P4 adiabatic, and when you put the value of 25 in this expression, it will reduce to a constant value 1.303. This is H2 for acetaldehyde. And for ethanol, H4. Okay. So here we have to again do the same thing, but here CP value will be this, which we have already seen or written here. And when you solve it, you should get 4.958 into, sorry, it is 0.06134 P adiabatic plus 7.86 10 to the power minus 5 P square adiabatic, then 2.916 10 to the power minus 8 T cube adiabatic plus 4.958 10 to the power minus 12 t to the power 4, and the constant value is 1.582. And lastly, for hydrogen, which is H3 in our case, you have to substitute the value of Cp. Yes, so it is yeah. When you simplify it, you should get All right. And the constant value is minus 0.7210. So when you substitute all these values in this expression, that is delta H is equal to first number of moles of product it will be a long expression. Let's write it for H2, that is first acetaldehyde. So 50 into H2 hat. And here delta H is 0 because the process is adiabatic. Then another product is hydrogen. So it is H3 hat minus minus H4, sorry, the product there is ethanol, some ethanol is also coming out. So H4 hat will also be there. And 100 moles of H1, H1 hat. Okay. Plus your extent of reaction, yeah, this term, which is will be 3445.5. So here you will get an expression in terms of the adiabatic, and then the adiabatic value will be obtained. You can use a solver for doing this. So I'm using an online solver for solving this expression. Shouldn't take too much of time. So So if you put this equation, this big equation into a solver, you should be able to get T adiabatic. This is a very, I tried to write it and all, it's a very big expression. So this is a homework for you guys. Solve it and let me know what is the adiabatic value that you're getting. All right. So that's it for today's class. It went too long than expected. I'll see you the next week, and with in the next week class we will discuss the last topic of this course, and with this that next week will be our last meeting. So if you are available, please try to join, and we can maybe discuss a bit more if you have any more doubts or anything like that. So thank you for joining. See you all in the next week.